In section 8.5, we discussed applications to physics, and really the most specific one, or the one that we talked the most about, was this idea of work. And so what we said is work done on a particular object is equivalent to the force put on that object times the distance that we're moving that object. And so essentially what we're going to do is we're going to use our definite integrals to do a sum of very, very infinitely small distances. So in this first example, it says the force F required to compress a spring by a distance x in meters from its equilibrium position is given by F equals kx for some constant k. Find the work done in compressing the spring 0.2 meters if k equals 10 newtons per meter. So what we're going to do is think about pushing this thing in infinitely small distances. So we're going to do this infinite number of small pushes, let's say. So let's think about a small push. The work done for a small push would equal the force. Well, they're telling us k is 10 and force equals kx. So the force is simply 10x. And our distance of this small push is going to be the smallest distance we can possibly imagine, which is dx or delta x. So that's our force for one small push. We're going to do this for a total of 0.2 meters. So from 0 to 0.2, 10x dx. And if we compute that value, we'll get 0.2. And remember, our units here are going to be what we call joules because we're using newtons and meters. Okay, in this example, an anchor weighing 100 pounds in water is attached to a chain weighing 3 pounds per foot in the water. Find the work done in hauling the anchor and chain to the surface of the water from a depth of 25 feet. So in this case, since we're pulling something up, work equals force times distance. In this case, we're using pounds. And when we're using that British systems of pounds, they already kind of factor gravity into the idea of force. And so here, force is equivalent to whatever the weight of the object is times the distance you're moving it. So the force is just going to be the weight of the object. Okay, so let's draw a picture so we can understand what's happening. So let's say we're on some boat. And this anchor was 25 feet down to the bottom. But at some moment in time, once we've started pulling this thing, here's our anchor. Once we've started pulling this anchor up, let's think about what's happening. We're going to add up an infinite number of small pulls. So let's think about the work that's being done in a small pull. Okay? The work would be the weight of that small pull times the distance that we make that pull happen. So at some moment, this thing is X meters up, right? And we're pulling it. We want to think about our next pull and the force that's being applied there. The force is going to be the weight of the anchor plus the weight of the chain. And then we're going to multiply that by the distance of the small pull. The distance is going to be dx. So the anchor, the weight of the anchor is not changing. It is a constant weight. It's going to be 100 pounds no matter what. However, for our moment, for our pull, that chain, the length of the chain is going to be 25 minus x. Would be the length of that chain at this moment because we've already pulled the anchor up x feet. And then we know the chain has a weight of 3 pounds per foot. So if the chain's length is 25 minus x, we want to multiply that by 3 to get the weight of the chain. So our work for a small pool is going to be 100 plus 75 minus 3x times the distance is just dx. Or in other words, the work for one infinitely small pool is 175 minus 3x dx. We want to do an infinite number of these small pools over 25 feet. So we're going to do the definite integral from 0 to 25 of 175 minus 3x dx. And if you compute that value, you'll get 3,437.5. And the units here, since we're talking about feet and pounds, are foot-pounds. Now, something that I want you to keep in mind, and you need to go back in your notes and look at this. Think about the international system. International system. And remember, when they were talking about their objects, they only consider mass, and then you need to additionally multiply in the force being applied by gravity. So go back and check those notes out and think about how the international system applies differently. And if you remember right, we said in there that you actually had to multiply in that 9.8 number, I believe. So go back and give that a look in case that were to show up on your test.